In section 8.1, we are working to find the area between two curves. And I'm not going to read all of the text that is on page 113, but in a moment I'm going to insist that you pause the video and stop and read all of the text that's on page 113. But we know back from when we first learned Riemann sums that if we are finding an area, we could approximate it by adding the sums of all of the rectangles between some point A, which is an x value, so like x sub A, and some point B, which is another x value. Well, if we're finding the area between two curves, let's say that f is the curve on top, and g is the name of the curve on bottom, we could think about kind of two different ways. We could think about first like finding the area of f. So like let's say that I want to find the area of f from A to B. Oops, that's B. And we could actually find that area, right? It would look kind of like this. Oh, it's a great drawing. And we could subtract from that the area that's under G, right? So like if this is my curve G, let's just pretend it looks like in the picture. If I find the area between G and the x-axis, I could think of that as subtraction. So one way to consider what we're doing when we find the area between curves is that we're going to integrate some function f from A to B, and we're going to subtract from that the definite integral from some function g from A to B. But we know that we could consolidate that under one integrand, right? F of x minus g of x. So another way to consider that though is that the height of each of these rectangles in the diagram, like f of whatever this x value is, like this point up here on the curve, this is f of some particular x value. And g, the function g at some particular x value, has a height down here. So the length of this rectangle here is just f of that particular x value minus g of that particular x value. And that will remain true for the entire integral as long as f stays on top. And we'll see in some examples when we have to consider that maybe f is not always on top. Okay, so again, I would encourage you to read the text that's on this page, but our big takeaway is that we can find the area between two curves on a closed interval by basically subtracting the top curve minus the bottom curve. And when we set up our integral, our area formula, excuse me, should look like this. Okay, so we said these notes underneath are always really important. So the note is that you always want to integrate top minus bottom when we are integrating with respect to x. We will also look at some examples where we integrate with respect to y. Okay, so I would say please pause the video if you haven't yet and actually read that text, but we're going to jump straight into some examples. So on page 114, we are asked to find the area of the region bounded by, we have two curves. We have the curve x squared plus 3, and we have another curve. I'm trying to move this tool out of my way so I can write y equals x minus, or sorry, 6 minus 2x. And you know what? I call that a curve, but we can tell that that's going to be a line. All right, so it would be very helpful if we knew what this looked like. And I do believe we could probably sketch these. We know what the quadratic and linear parent functions look like. We know how to apply transformations. So x squared plus 3, I'm just going to do a little sketch out here. That's going to be a parabola that is the parent function, but translated up 3 units. So again, we could think of from Algebra 2 how we learn our transformations, that A would be our stretch factor, if there is one, H is our horizontal shift, and K is our vertical shift. So we have just shifted this parabola up vertically, and I might even label this as 0, 3. And then we would also want to consider the line 6 minus 2x. And I'm just going to sketch a line with a negative slope. Say like, okay, this line, I'm going to say that 0, 6 is 6 minus 2x. All right, so when we read this question, when it says find the area of the region bounded by x squared plus 3 and 6 minus 2x, we're not given particular values a and b from which to integrate. We're going to have to find those. But if we look at our sketch of our graph we just did, the bounded region is the region that is contained between those two things. So if I kind of outline my parabola in my line here, we're trying to find the area of this region right here. Any other, like if I look outside of those intersections to any other region, those are going to be unbounded. So what I mean by that is, like, if we looked over here, that area, if I like shaded that on a graph, that plane would go on forever. Or like inside of the parabola, but above the line, I could shade forever in that direction. Same over here, I could shade forever below the line outside of the parabola. So bounded, we could think of that as meaning as like it's contained. Okay, so we have to figure out where those two intersections are. Like that's not given to us in this problem. So mathematically, and we are going to do this without a calculator, we need to set these two expressions equal to one another. So I'm looking for where x squared plus 3 is equal to 6 minus 2x. And we're going kind of stepping back into Algebra 1, Algebra 2 for a moment. This is a quadratic equation that we just made. It has a linear term as well, the negative 2x. And so anytime I'm solving a quadratic with a linear term, I'm going to have to get that equal to 0 and either use the zero product property, or sometimes I have to use the quadratic formula, but I must get this set equal to 0. So I'm going to rewrite this. I'm going to add the 2x to both sides, and I'm also going to subtract 6 from both sides, so that now we have a quadratic equation that is set equal to 0. And using the zero product property, factoring will help me because I need factors to have a product. So all right, I know if I'm factoring something with an x squared, it's 1x squared, so I need x and x. If I think what multiplies to negative 3 and adds to positive 2, I get a plus 3 and a minus 1. So using the zero product property, we could solve for x, and we know if x plus 3 is 0, x equals negative 3. If x minus 1 is 0, x equals positive 1. Okay, so we have the x values of that intersection, and since we're going to integrate with respect to x, that is all we need to get started. It doesn't hurt to find the y values. If I were to just plug those x values back into either of these original equations here, like x squared plus 3, well, negative 3 squared plus 3 is 9 plus 3, which is 12. So sometimes it helps me to know the y value of that ordered pair. And then over here, if I look at this intersection, 1 squared plus 3 is 4. So this is the ordered pair 1, 4. You could have also used the linear equation to find those y values. Okay, so now if I think what is on top, well, the thing that's on top is going to be the line. Like I'm just literally looking at that bounded region. And I want to point out the line is not always on top of the parabola. I'm only looking in this bounded area. So what I like to do is I like to draw a little test rectangle. I'm going to really encourage you to do this. As these get harder, this is really helpful. And this is also going to be really helpful for what we do in 8.2. And 8.2 is no joke, y'all. So all right, so here's my rectangle. And if I think about the height of this rectangle, at any point in, not time, but any point on the x-axis between the intersections, so between x equals negative 3 and x equals positive 1, anywhere in there, the height of this rectangle is always going to be my line minus my parabola. So going back to that formula, you could think of this as your f of x. You could think of this as your g of x, but I'm not going to write it that way. I'm just going to say that the height of this is 6 minus 2x. These parentheses aren't super necessary. I just kind of like to group it together to say like, hey, that's my f, but then minus Now these parentheses are super necessary coming after a subtraction sign when we have grouping, minus g of x, so minus x squared plus 3. Okay, so when we are finding our area now, that is going to be our integrand. That is our f minus g. That is what is going to give us the height of any rectangle in that bounded region. So to find our area, we want to integrate from left to right, so from -3 to +1, and we want f minus g. So we want our 6 minus 2x, that is f, minus x squared plus 3, that is g. And absolutely the first thing I'm going to do is distribute that negative so I can drop those parentheses. So this is 6 minus 2x minus x squared minus 3. And I am probably also going to want to combine any like terms that I can there. So, and you don't have to do it this way, but I like to rewrite this into standard form. So I'm going to put my negative x squared out first. The standard form is kind of optional, just my brain really wants to do that. Then my linear term, which is negative 2x. And then when I combine my 6 minus 3, I have a positive 3 still. And I personally am not going to like factor out a negative or anything. I'm just going to leave it like this. You can factor out a negative if it bothers you. So, all right, so as we go to find our area, I also want you to pay attention that so far, everything I've written down, I have linked with equal signs because these things are literally equal. And again, the expectation for showing our work is constructing a viable argument. So as I go to find this area, I need an equal sign here as I go to find my antiderivative. Okay, so now we are just back in like unit 6 stuff. How do I integrate? Well, I'm going to use the power rule since I have a polynomial function. So I'm going to add 1 to my exponent and divide by my new exponent. New exponent. Let's see, for negative 2x, that becomes negative x squared when I do that. And then we get a plus 3x there. Okay, so when we go to evaluate this, from -3 to 1, I'm going to use my equal sign again because this shows now that I'm going to evaluate this integral. I always plug in top minus bottom, right? Because what we're using is the fundamental theorem of calculus when we do this, that if we integrate some function, we find its antiderivative, we plug in the top, we plug in the bottom, and we subtract. Okay, so I'm going to plug in the 1. Let's see, so that's -1/3, well, times 1 cubed. Well, that's just a positive 1, minus 1 squared, plus 3 times 1. And then I'm going to subtract from that. And again, these parentheses are not optional because I'm going to have multiple terms. I'm going to subtract from that -1/3 times -3 cubed. I'm not going to do that one in my head just yet. I'm going to write it down first. Minus -3 squared plus 3 times -3. And like a quick reminder, anytime we substitute a negative, we always put it in parentheses. Otherwise, we might mess up the order of operations part that comes next. Okay, so that is -1/3 minus 1 plus 3. I'm just going to call that a plus 2 for right now. Minus, let's see, over here, -3 cubed, let's see, 3 times 3 is 9, times another 3 is 27, but since I'm multiplying 3 negative 3's, that's going to become a -27. -1/3 times -27 is positive 9. All right, then right here I have -3 squared, which is positive 9, but it's getting subtracted, so 9 minus 9, and then 3 times -3 is a -9, so plus a -9 here. All right, so we get -1/3 plus 2, 9 minus 9 is just minus 9. Let's see, and that ends up being like 11. Oh, wait. So I almost did something silly. Okay, I forgot to drop my parentheses and distribute the negative. This is a plus 9 because we're subtracting a negative there. All right, so we end up getting 11 minus 1/3. And on a free response question, you can absolutely leave your answer like that. That is 32 thirds. Okay, so this first example I think is fairly easy. We are going to look at a couple more examples, and I'm going to encourage you guys not to skip any of them. I know it's a lot, but Unit 8's pretty important. So